In topic 3.11, we're introducing the secant, cosecant, and cotangent functions. So these are new functions for you that you may have not heard of before. So let's think back of some things that we already know. In topic 3.9, we learned about inverse trig functions. That's the ones where you input a value, you get out an angle measurement. Well, today we're discussing the reciprocal functions. Now, these are not the same things. It's really tempting to say that they are, but they are completely different functions. In fact, secant, cosecant, and cotangent are their own trig functions themselves. Because they're reciprocals, like regular reciprocal numbers where you flip over the fraction, these are going to be flipped over versions of sine, cosine, and tangent. And since we have created rational functions, some of the rules from chapter 1 with rational functions comes back. There will be input values that cause the function to become undefined or make that denominator 0. And at these points, these graphs are going to have vertical asymptotes appear on the graph. So we're going to be looking for these vertical asymptotes today because they help us graph these functions. Now, the secant function, which has a shorthand of SEC, the secant function is the reciprocal of the cosine function. So it is 1 over cosine of theta. Since cosine of theta is x divided by the radius, secant function is the radius divided by x, just the reciprocal value from cosine. So in example 1, we're going to need to rely on having our unit circle a lot. So go ahead and get out that unit circle that's somewhere in your lovely binder that I know you're keeping up with for my class. And let's look up some of these values. Now on your unit circle, find the angle pi over 6. The angle pi over 6 has a coordinate point associated with it that has the cosine values and then the sine values. Well, that cosine value, we're just going to take the reciprocal of that number. So looking at your unit circle, at pi over 6, the cosine value there is square root of 3 over 2. Now notice I wrote the reciprocal of that value because secant is just the flipped over fraction for the value of cosine of pi over 6. But of course, you know me, I don't want my answer to have an irrational denominator. So we're going to go ahead and rationalize by multiplying by root 3 over 3 on both the top and bottom. And so we get that the value of secant of pi over 6 is 2 square root of 3 over 3. Moving on to secant of 3 pi over 4. Again, look at your unit circle for where the angle measurement 3 pi over 4 is. The first coordinate point there, once you find it, is negative square root of 2 over 2. Notice again, I wrote it as its reciprocal because this is secant, not cosine. When we rationalize this denominator, multiplying by square root of 2 on both the top and bottom, you end up with negative 2 square root of 2 divided by 2. Poof, those 2's will cancel out. You end up with negative square root 2. For question C, again, go on your unit circle to the to pi over 2. And I want that first coordinate. Well, the first coordinate of secant is 0. That means that this is 1 over 0. If you are dividing by 0, that is undefined. So the reciprocal of 0 is undefined and vice versa. So at secant of pi over 2, there's going to be an undefined value. If you think back to rational functions, that means that we will eventually see a vertical asymptote appearing at pi over 2. Now go to 0 on your unit circle. At 0, the first coordinate point there is 1. Well, what is the reciprocal of 1? It's still 1. So the secant of 0 is 1. Now what this means is that all around the unit circle, which creates the graphs of these functions, we can just take the cosine values and use their reciprocals. So to create the graph of the secant function, I have here plotted for you x values, and I've written in the cosine values associated with those around the unit circle. I've picked the ones that I wanted us to pay attention to. You'll see why in just a little bit. Now let's write the secant of these values. So again, all I'm going to do is take the reciprocal of this row, which is the reciprocal of cosine. The reciprocal of 1 is 1. The reciprocal of 1 over 2 is 2. The reciprocal of 0 is undefined. The reciprocal of negative 1 over 2 is negative 2, negative 1, negative 2. You see what's happening here? So we do have a pattern to these numbers. Pattern is just different for this periodic function. Let's look at what this looks like on a graph. Now, when I'm graphing these, I actually like to start with my vertical asymptotes. So at pi over 2, and at 3 pi over 2, where I got those undefined values, I'm going to draw in my vertical asymptotes. Remember, vertical asymptotes are invisible vertical lines that the graph is going to approach but never actually touch. So we can get close, but we cannot touch or cross these dashed orange lines that I've put down in the middle of our graph. Notice this is where the cosine function, which I've plotted for you, is crossing the x-axis, or is crossing our midline. That's going to be important to remember. Now, if we plot the other points we have at 1, we'd be at 1. Okay, those kind of overlap a little bit. At pi over 3, we're at 2, and then we have our undefined value. At 2 pi over 3, you jump down to -2, and then 2, and then -2 again. Undefined, so there's my vertical asymptote. At 5 pi over 3, we're up at 2, and at 2 pi, we're back at 1. What's interesting about this is when I play connect the dots here, and I actually connect these graphs together, it creates, and this is not like really good vocabulary, but visually for me, it makes these bowls. And these bowls are what the shape of the secant function is. This is one period of the secant function. It's the reciprocal of cosine. So I have my cosine function, and I have the reciprocal, which is secant, graphed with it. Things I need you to pay attention to that will help you graph these functions later is, again, paying attention to those vertical asymptotes. There are going to be vertical asymptotes at places where cosine of theta is equal to 0. So as long as you pay attention to these places right here where cosine of theta is equal to 0, you'll be able to identify all of our vertical asymptotes and create the bowls in between them. When we graph secant functions, we actually are always going to graph the cosine function in between it just to make sure that the values make sense and that they are actually reciprocals. But let's talk some information about this function. The domain of this function is all real numbers except the places where there are vertical asymptotes. So it's all real numbers except x is not allowed to be equal to the place where I first see a vertical asymptote, pi over 2, and every vertical asymptote after that, which occurs every pi distance away. So we say that the domain is x not equal to pi over 2 plus pi k, given k is an integer. Because that means I can use every value except for every repetition of this vertical asymptote as we keep scrolling left and right on this graph. The range is the reciprocal, or the outsides, I like to think of it, of the range of the cosine function. Cosine is bounded as a low point at -1 and a high point at 1. So the range of secant is literally everything else, which means we go from -infinity all the way up to -1. Then we have a gap in the middle, pick back up at 1 and go to positive infinity. This little gap in the middle is the range of cosine. So the range of secant is everything else. As you can see, this shape repeats every 2 pi, so it has a period of 2 pi. And it has vertical asymptotes at every place we said the domain was undefined. So pi over 2 plus pi times k, given k is an integer. And again, I'm using shorthand for the phrase k is an integer. You can write out those words if those symbols don't mean anything to you. Looking at only the blue part, so I know it's confusing because I graphed cosine on this graph as well, but that's just my guide to graph secant. There are no x-intercepts for secant. There are no places it crosses the middle line. That's where it's undefined. There are also no minimum and maximum values since those arrows go off screen, positive and negatively, to infinity, and it has no amplitude. But we can think about the fact that the cosine function it relates to does have maxes and mins and does have an amplitude. So secant and cosecant won't have amplitudes, but their related functions will. Because I could take this function and fold it along the y-axis, when I fold it along the y-axis, that means it's symmetrical to the y-axis, and that means that this is an even function. That is the graph of the secant function. Let's talk about the cosecant function. You can probably estimate what's happening here. The cosecant function, which has a shorthand like this, CSC of theta, so cosecant of theta, is the reciprocal of sine. And since sine is y divided by the radius, that means that cosecant is the radius divided by y, just the reciprocal of those values. So again, let's look around our unit circle for these values. Since sine is the second coordinate, or the y-coordinate around the unit circle, I need you to find the y-coordinate at pi over 6, and then we're going to use the reciprocal. Sine of pi over 6 is 1/2. Notice again, I wrote it as its reciprocal of 2 over 1. So cosecant of pi over 6 is just 2. On my unit circle, find 3 pi over 4. The sine coordinate at 3 pi over 4 is square root of 2 over 2. I wrote it as its reciprocal, and then we just rationalize my denominator. Multiply by square root 2 on both top and bottom, and then those 2's are going to cancel out. I get that the cosecant of 3 pi over 4 is square root of 2. All of this is coming from the unit circle. Find pi over 2 on your unit circle. The y-coordinate at pi over 2 is 1. The reciprocal of 1 is still 1. And so the cosecant of pi over 2 is 1. Last but not least, find 0 on your unit circle. The second coordinate on that coordinate point at 0 is 0, which the reciprocal of 0 is undefined. So there are also going to be values here in this function where we'll have vertical asymptotes, because there are places where sine is equal to 0, which makes my denominator equal to 0, which means I have a vertical asymptote. Let's do the same thing we did for the secant function in the front page for the cosecant function here. And again, I've already graphed sine, and I have the points for sine plotted. All we need to do is take the reciprocal of each of these values so that we know the cosecant value. Well, the reciprocal of 0 is undefined. The reciprocal of 1/2 is 2. The reciprocal of 1 is 1, and then 2, and then undefined. I think you can kind of see the pattern here. Reciprocal -2, -1, -2, and undefined. Now when I'm graphing these functions, like I said earlier, I like to start not only with having sine, but having these values where the vertical asymptotes appear and going ahead and graphing those vertical asymptotes. So I know my boundaries on the left and right that I'm not allowed to cross once I start doing those. You can't see me because this is a video lesson, but I'm air quoting the words bowls for both the top and bottom bowls for secant and cosecant. Okay, those are the places where sine is equal to 0. So that's the places I have a vertical asymptote. Let's plot the points in between. At pi over 6, we have 2. At pi over 2, 1. 5 pi over 6, 2. And then 7 pi over 6 is -2. And then 1. And then -2. So when I play connect the dots here, for one period of the cosecant function, these are what the bowls are going to look like. They're the reciprocals of the sine function. So some things to think about here. Your vertical asymptotes for this graph are going to appear when sine of theta is equal to 0, because that's what would make my denominator equal to 0. So when it crosses that midline. Let's talk through some points of interest about this function. Like the secant function, the cosecant function has all these breaks in its domain. So its domain is all real numbers except that x cannot be equal to 0 and any pi repetition after that, given k is an integer. So I say x is not equal to 0 plus pi times k. Since every pi distance on my x-axis, I have a vertical asymptote. The range is the everything else that sine does not cover. And since sine normally goes from -1 to 1, the range of the cosecant graph is going to be from -infinity to -1, and then from 1 to infinity. Again, this little break in the middle, this gap, is the range of sine. So the range of cosecant is just literally everything else. Since this shape takes a whole 2 pi to finish, having an upward-facing bowl and a downward-facing bowl, the period of the cosecant function is 2 pi, and the graph has those vertical asymptotes at every place I said there would be a break in the domain, which is 0 plus pi k, given k is an integer. Like secant, cosecant has no x-intercepts, no maxes and mins, and no amplitude, but the sine function it relates to does have all of those things. So that's important for us to remember. Again, this is related to sine. Sine has all of these values, and cosecant is just a reciprocal of it. Hard to tell on this graph because I only plotted from 0 to 2 pi, but if I were to plot from negative 2 pi to 2 pi, you'd see that this function can be rotated around the origin, so it's symmetrical about the origin, and land right on top of each other, which means that this is an odd function. This is the graph of cosecant, the reciprocal of sine. The last graph we're going to be graphing here, the last reciprocal function, is the cotangent function. This one's named very aptly because obviously cotangent, COT, again, please do not say cot of theta. That is not how you pronounce this. This is cotangent of theta, pet peeve of mine. Cotangent of theta is just the reciprocal of tangent, so 1 over tangent. Since tangent is y divided by x, that means cotangent is x divided by y. And since tangent is sine divided by cosine, this means that this cotangent is cosine divided by sine. So when we do this one across the unit circle, you can look at those values of the unit circle, yes, because we have the coordinates cosine, comma sine. Or if you remember your values from the hand trick or from the table I had you memorize, that might make this next little bit easier. If we're thinking about the cotangent of pi over 6, it's like thinking about the tangent of pi over 6. If you're thinking tangent of pi over 6 and you have it memorized from what I've asked you to memorize, it would be square root of 3 over 3. I'm using the reciprocal of that since this is cotangent. But of course, I need to rationalize my denominator, so I multiply by square root 3 on top and bottom and cancel out those 3's that they have in common on top and bottom, and voila, I have square root of 3. Thinking about the cotangent of 3 pi over 4, well, that's a quadrant 2 angle, so I know tangent would be negative there. And tangent of pi over 4 is 1. The reciprocal of that is still just 1. The cotangent of pi over 2. Now, the tangent of pi over 2, if you think about the sine and cosine values around the unit circle, that would mean that cotangent is the cosine divided by sine. Well, at pi over 2, cosine is 0, and sine is 1, which means that the cotangent of pi over 2 is 0. But if we go look at 0 on my unit circle, cosine divided by sine here would give me 1 divided by 0, and that's where I'm going to have yet another undefined value. So let's think about what the graph of the cotangent function might look like. So again, I have plotted, or I have a table of values here for you. I'll have x values, I have tangent values. We're going to fill in the cotangent values. So let's go ahead and find some of these values. Remember, we're just doing the reciprocal of each of these values. The reciprocal of 0 is undefined. The reciprocal of 1 is 1. And the reciprocal of something that's undefined is actually 0. So pause for a second. Remember, undefined means that we took some number and we divided it by 0. So the reciprocal of that becomes 0 over 1, which is just the number 0. Okay? The reciprocal of negative 1 is negative 1. The reciprocal of 0 is undefined. The reciprocal of 1 is 1, the reciprocal of undefined is 0, and then negative 1, and then undefined. So interesting. I'm going to have a very weird looking graph here, but if you remember the shape of tangent, this might not be that weird. So here are the places where this graph is going to be undefined. It'll be at 0, there's my vertical asymptote. It will be at pi, here's a vertical asymptote, and it'll be at 2 pi, another vertical asymptote. If I plot the points I have, pi over 4, comma 1, pi over 2, comma 0, 3 pi over 4, comma negative 1, 5 over 4, comma 1, 3 pi over 2, comma 0, 7 pi over 4, negative 1. When I play connect the dots here, this graph is going to look like the tangent function except different. Remember, our tangent function were like those stretched out s's. This is also like some stretched out s's, but they're just shifted and these are decreasing. Tangent was a constantly increasing function because all of those S shapes did like this, increasing over and over again. Cotangent is a decreasing function. it has vertical asymptotes in different spaces. Now this is going to be important that we notice that the vertical asymptotes of this graph are going to appear at x equal to 0, x equal to pi, and x equal to 2 pi, and on and on. Every multiple of pi, there will be a vertical asymptote. This will help us be able to graph transformations of these functions if we remember that the vertical asymptotes appear at multiples of pi for cotangent. Let's talk about the domain and range and all of this information for cotangent. The domain, since we have all of these breaks in the graph, would be all real numbers except when x is equal to some multiple of pi. So 0 plus pi k given k is an integer. The range, those arrows go all the way down and all the way up, which means this is from negative infinity to infinity. There is no boundary on this one's range. The period of the cotangent function, ooh, interesting. Let's think about how long it takes for this shape to repeat. It only takes this distance on the graph to repeat, which means that the period of the cotangent is just pi, which makes sense because the period of tangent is pi, so the period of cotangent is pi. The graph will have these vertical asymptotes at every place there's a discontinuity in the domain, which is at 0 plus pi times k, given k is an integer. And the x values of this graph are of the form x equal to pi over 2 plus pi times k. Again, this is the first place I see an x-intercept show up, boom. And this is the distance or the period till I see it again, boom, that's pi. Like tangent, there is no maxes and min values and it has no amplitude. When we're graphing it, these little points right here, they're not amplitude. When we were in class, I air quoted the word amplitude there. It is not an amplitude, but you can think of it as the intermediate values. This is affected by any number put in front of the tangent as a vertical dilation. This is what it's changing, like the amplitude changed for sine and cosine. But technically, tangent and cotangent have no amplitude. This function is also symmetric to the origin, since we can rotate it around the origin and it would look the same. Therefore, it is an odd function. So we have these three new types of functions we can graph, and that's what we're going to be really focusing on today, is being able to graph the secant, cosecant, and cotangent functions given some different transformations. So here we go. Our first graph that we're going to graph only on the interval from 0 to 2 pi is y equal to 2 secant of 2x. Now we're advanced enough in our ability to plot transformations that I'm going to go a little quickly over the things that we've talked about before, meaning I want to know what graph it's related to and any changes from that regular graph. 2 secant of 2x is related to 2 cosine of 2x because cosine and secant are reciprocals. And if I were plotting 2 cosine of 2x, I would notice that the amplitude would be 2 and that this b value would be 2, which tells me that the period of this function is 2 pi divided by 2, or is just pi. So I should repeat an entire shape, an entire period between 0 and pi. But this question asks me to plot until 2 pi, so I'm going to go ahead and do that. I didn't put this right in the middle, so I'm going to do that. That looks better. Okay. I know that I now, going from 0 to 2 pi, should see 2 whole repeats of this function, since that's the period. I also know that the cosine function that I am related to when I'm graphing secant has an amplitude of 2. So if I were just plotting the cosine function, just the cosine function, not the secant function, I know that I should finish the whole shape between 0 and pi, which means I need to have 4 subintervals for a maximum, middle, minimum, middle, and maximum, and then I can repeat that to make the other period so that I can go ahead and graph this whole thing. Max, middle, min, middle, max. Okay, I'm doing this in black on purpose, and if you have 2 colored pencils, do this in like pencil color, all right? This is the cosine function. That was not our goal to graph. Our goal was to graph the secant version of this. Our goal is to graph 2 secant of 2x. So we need to think about how this secant function is related to cosine. It is related, number one, that every place there is a 0 for cosine, there is a vertical asymptote for secant. So I can come in and every place I had a middle value or I had an x-intercept. That is where I'm going to draw in my vertical asymptotes. So for this graph, we got a lot of vertical asymptotes happening. In between those vertical asymptotes, I know that there's going to be reciprocal values, or those bowl values showing up. So I hit the old amplitude, the old max and min of sine and cosine, and create my bowls. You see how I'm doing that? So these values should be the same. They share that max and min value from the cosine function, and then the bowl just has to not cross the vertical asymptote. And voila, that's secant. Now, there's a whole lot of other things we can do to make this more accurate. We obviously could plot more points. We could use a graphing calculator to get way more accurate, but this is a good sketch for the function for me. We're starting with the appropriate related trig function and how we've graphed those before with amplitude, period, phase shift, and midline shift, and all of that good stuff. And then we're just reciprocaling it. That's not a verb. We're using the reciprocal. For number B, we think about the related function. We are actually going to plot y equal to -3 sine of x plus 2 so that we can know what it's supposed to look like before we do the reciprocal. Now for this one, I know that this means it has an amplitude of 3 and a reflection since the a is -3. I also know that the midline has changed to 2. So that's the A and the D. So if I go ahead and just do that, now there's going to be a lot of dashed lines here just because I like to see my midline. So I'm drawing a purple midline here. If that amount of dashed lines once we draw on the vertical asymptotes is confusing to you, you don't have to draw the midline. I find them very helpful. Now my period didn't change here, so I really should just have one full sine wave between 0 and 2 pi. So I'm going to hit all of the normal quadrantial angles, which is pi over 2, pi, 3 pi over 2, and 2 pi. And draw a sine. Now the sine should have an amplitude of 3 and be reflected. So 1, 2, 3. This is going to be the lowest point, and then 1, 2, 3. This is going to be the highest point. So sine. Sine starts in the center, but since this is reflected, instead of going up, I'm going to go down and then back to the center, and then up and then back to the center. So this is the cosine wave that is related to the function we're graphing. But remember, we are graphing -3 cosecant of x plus 2, which means everywhere there was a midline or a center point for the sine function, there is now going to be a vertical asymptote. So not necessarily just where it crosses the x-axis, but where it crosses its center line, that's where you put your vertical asymptotes. That's why I like to draw the purple center line. For me, visually, it helps. After that, I just need you to connect to the bowls. So the ones that are low points for sine create opening down bowls for the cosecant, and then opening up. Again, bowls is not a really big mathematical word, but it makes visual sense to me, so that's what I'm going to continue to call it. The next graph is y equals cotangent of x over 2. Ooh, cotangent is different since it doesn't have a related like sine or cosine function for us to just do the reciprocals of. We need to think about the location of the vertical asymptotes for this decreasing function. Now, the vertical asymptotes are going to appear anywhere the insides of this function, this is where the vertical asymptotes are, is equal to 0 and equal to pi. Also 2 pi. Well, you'll see why I didn't put that one down. If we solve for x, that means we're multiplying by 2 on both sides. This one would give me 0. This one would give me 2 pi. So for this change in the period, this means that we're only going to have vertical asymptotes appearing at 0 and at 2 pi, which I'll label my graph here in a second. This is a stretched out graph, horizontally stretched graph for cotangent. Now, cotangent should be decreasing, and there are 3 points of interest in between the vertical asymptotes. So smack in the middle, you should have a middle point. This has not been translated up and down, so I know that I have a middle point, boom, right there. Evenly spaced out between that, you also have the other 2 important values, which, since this is decreasing, should be at 1 and at -1, meaning I have a high point, middle point, low point. It's really tempting when you graph cotangent to kind of make it look like a slanted line. Remember, they're still curves, so there does need to be curve here and here if you can't make the curves happen here because we're not computers. But it should still be curvy, not super straight, because these are not linear functions. The last function we're going to be graphing is y equal to 1/2 secant of x minus 2. So again, we're going to use another one of the functions as a guide. We're going to be using 1/2 cosine of x minus pi over 2 as a guide to be able to draw the reciprocal function. Looking at this, we know that the a value is 1/2, so we have vertically shrunk this function. It has a different amplitude, and we see that there is a phase shift. This phase shift is negative pi over 2, which means we're going to be moving this graph to the right. So when we set up our x-axis here, going all the way to 2 pi, we know that this typically has quadrantial angles or important points at pi over 2, at pi, and at 3 pi over 2, in between 0 and 2 pi. So plotting my amplitude is going to be at 1/2. I'm just going to draw 1 and -1 so I know to make my amplitudes halfway in between that. That means that my maximum for this cosine function is not going to start at 0, but is going to start at pi over 2 to the right. And then I will go to a center, and then I will go to a minimum, and then I will go to a center. Let me make my minimum actually look like a minimum here. And then back to a center. So my cosine function looks something like this. Shifted to the right pi over 2 units. Now, of course, we want to know where the vertical asymptotes for these for the secant function would happen, which would be at all the places that cosine has a 0 or has a center point, which is at 0 and at pi and at 2 pi. So our secant function will just occur in between those. So my secant function will look something like this. The last example here on your notes is going to talk about, without graphing the function, we are going to determine the location of the vertical asymptotes between 0 and 2 pi, and then determine the range of the function. Now your homework is going to also ask you to find the period, so you can flip back to other questions here to determine how the b value of your function affects the period. But if we're determining the location of the vertical asymptotes, we know that the vertical asymptotes for the cosecant function are going to occur where sine is equal to 0. So if we think about the sine curve, sine is equal to 0 when it is equal to 0, when it is equal to pi, and when the function is equal to 2 pi. So if I solve each of these things, this would end up giving me x equal to 0, x equal to 2 pi, and x equal to 4 pi. I'm solving for x, by the way, multiplying by 2 on both sides. So the locations of the vertical asymptotes are going to appear at the x values of 0 and at 2 pi only. Now I'm not answering 4 pi just specifically because this question only wants us to use the domain interval from 0 to 2 pi, which means that 4 pi is beyond this graph. We're not looking at 4 pi, we're just looking between 0 and 4 pi. Sorry, 0 and 2 pi. To find the range of this function, what we're going to do is we're going to think of g of x as its reciprocal. So 2 cosecant of x divided by 2 plus 1. It has a related function, which would be 2 sine of x over 2 plus 1. Well, based on these numbers, I know that sine has been moved up and then has an amplitude of 2, which means it reaches a maximum of 3 and a minimum of -1. So 1 plus 2 is 3, 1 minus 2 is -1, which means that our sine function has a range from -1 to 3. So again, that is 1 minus 2 is -1, 1 plus 2 is 3. Which then means that our function g of x is going to have a range that is just the reciprocal of those, or outside of that boundary. So our range is from -infinity to -1, and then from 3 to +infinity. So again, if we think about its reciprocal value, we're going to be able to determine the range of the function itself, since there's just literally everything else outside of that range. Now this last page here, if you notice, this is just kind of a summary page of the types of trig functions we've learned about so far. This column has the shapes, definitions, domains, and ranges of the three basic trig functions, sine, cosine, and tangent. This column has what we just learned about, which is the reciprocal functions, its definition, graph, and domain and range. And then I have our inverse functions here as well, just so you can see that these two things, reciprocal and inverse functions, are significantly different. Last thing before we go, this is hard for me to show you because again, I know I'm not there today and I can't show you a calculator, but if you notice, there is no button on your calculator for the reciprocal functions. You do not see a button that says secant. You do not see a button that says cosecant, and you do not see a button that says cotangent. So we actually have to remember how they're related to the reciprocal values to type them in. So if we're wanting to type secant either in a graph or to evaluate a function, you would actually have to type 1 divided by cosine and then whatever the value is for x. For cosecant, you would type 1 divided by sine of x. For cotangent, you would do 1 divided by tangent. So you're going to have to use either the fancy fraction or a bunch of parentheses here to get these functions to show up. Again, this is for evaluating in your calculator since there is no button for secant, cosecant, or cotangent. You use 1 divided by its reciprocal to get it to show up in a graph or to get it to evaluate a particular value in your calculator.